Welcome to This Explainer. Let's decode the Cambridge IGCSE laws of indices completely from first principles.
So, here's a mind bender for you. How do you multiply a number by itself -3 times?
First, the basic anatomy. In 5 to the power of 3, 5's the base, 3's the index.
The index literally just tells the base to multiply by itself that many times. Boom, 125.
That brings us to Law 1. Multiplying identical bases? Skip the heavy lifting and just add the indices.
Think about it. 4 cubed times 4 squared physically expands out to 4 to the power of 5.
Logically then, if multiplying adds indices, dividing identical bases means we just got to subtract them.
So instead of calculating huge numbers, 2 to the 5th divided by 2 cubed easily becomes 2 squared.
Okay, but what about a power raised to another power? Just multiply those indices right together.
Like 4 squared all cubed rapidly explodes into 4 to the 6th, or 4096.
Now, here's where things get super interesting. What if your index drops to exactly 0? Let's prove it logically. A to the m divided by itself gives us a to the m minus m.
And since any number divided by itself is just 1, anything to the power of 0 equals 1.
All right, circling back to our initial mind bender, what happens if the index drops below 0?
Subtracting m from 0 using our second law shows a negative index is really just a hidden division problem. So a to the negative m is quite simply 1 over a to the positive m.
Finally, the big one. How do we handle a fractional index, like 16 to the power of 1/2?
Using our third law, squaring this fraction just gives us 16 to the power of 1. Since 4 squared equals 16, raising 16 to the half is basically just finding the square root, 4. The main takeaway? A fractional index is literally just an instruction telling you to find the root. Let's crack a tough one, 25 to the 3/2. Just find the square root first, then cube that result. The square root of 25 is 5, and 5 cubed gets us to 125. Easy.
So here's your ultimate exam cheat sheet: the basic operations plus the zero, negative, and fractional rules.
If these complex rules stem from simple logical counting, what other math mysteries can we unravel from first principles?